Okay, so think about this for a second. You've got a simple factory conveyor belt, and you've got a super high-tech robotic arm. They're both powered by motors, but they do radically different jobs, right? One is like a marathon runner, just steady and consistent. The other is a precision surgeon. So what's the secret? Well, it's not really about the motors themselves, but the brains behind them. And understanding that difference, that's the key to understanding all sorts of modern automation.
So what we've got here are two very different tasks, but they share one big problem. How do you get an electric motor to do exactly what you need it to do when you need it to do it?
All right, so on one hand, just picture that classic industrial conveyor belt. Its job is pretty simple, right? Just run all day, every day, at a nice, steady speed. It's the workhorse of the factory. But then, on the other hand, you've got that robotic arm, and it's assembling something like a circuit board. It's got to be lightning fast, stopping and starting in the blink of an eye, placing these tiny little components with absolute pinpoint accuracy. It's basically the neurosurgeon of the assembly line.
Now, here's the real kicker. At their core, both of these machines are driven by pretty standard electric motors. So why can't you just use the same controller for both? Why does one get a simple, cheap solution while the other needs this complex, super high-performance system? Answering that question is really fundamental to getting how smart automation works today. So let's meet the two main players in this little puzzle, the variable frequency drive, which everyone just calls a VFD, and the servo motor system. First up is the VFD. The easiest way to think about this is like a really sophisticated dimmer switch, but for a standard off-the-shelf motor. See, an AC motor's speed is directly tied to the frequency of the electricity you feed it. The VFD is basically a translator. It takes the standard power from the wall and just dials the frequency up or down to make the motor spin faster or slower. It's the perfect, super cost-effective solution for our conveyor belt, where all we really care about is just holding a consistent speed. And then we have the servo motor system. And I gotta tell you, the key word here really is system. This isn't just one component. It's a whole team that's designed to work together perfectly. You've got a specialized motor, a smart drive, and this is the most important part, a feedback device. This is that high-performance setup our little robotic arm needs to get its incredible precision. So if you look at this table, you'll see the obvious differences, right? VFDs, they're really just about controlling speed. Servos, on the other hand, they give you precise control over position, speed, and torque. That's the motor's twisting force. And yeah, as you can see, all that extra control and precision, it comes with a higher price tag. But, these are really just the symptoms. The real difference, the secret that separates these two worlds, it boils down to one fundamental idea. And here it is. This is the secret ingredient, the one concept that truly separates these two technologies and makes all that incredible precision possible is feedback. Okay, to get this, let's talk about what we call an open-loop system. And honestly, the best analogy is your microwave. You tell it, run for 2 minutes, and it runs for exactly 2 minutes. It just assumes your food is going to be hot when it's done. It never actually checks the temperature, does it? Nope. It just runs the command and hopes for the best. It's totally a set-it-and-forget-it kind of approach. Now, let's contrast that with a closed-loop system. This is just like the cruise control in your car. You set it to 65 miles per hour. Now, the car doesn't just jam the gas pedal in one spot, right? It's constantly measuring your actual speed. If you start going up a hill and you slow down, it senses that error and it automatically gives the engine more gas to get you right back to 65. It's in this constant cycle. Measure, compare, correct. That little loop, that is the very definition of feedback. So right there, that's the big trade-off. Open loop is simple. It's cheap, but it's basically flying blind. It has no way to adapt if something unexpected happens. Closed loop, well, it's more complex and it costs more, but its huge advantage is accuracy, because it is always watching itself and making corrections. And that one difference changes everything when you're trying to control a motor. And this brings us right back to our VFDs and servos, because this whole idea completely reframes the choice. It's not just about speed versus position anymore, it's about two totally different philosophies of control. I love this quote because it just nails it. A standard VFD system is open loop. It sends out a command and it just assumes the motor is doing what it's told. But a servo system, it's closed loop. It doesn't assume anything. It knows. It knows exactly where that motor shaft is and what it's doing, every single millisecond. So how does it know all this stuff? It's having this constant, high-speed conversation through a little feedback device called an encoder. You can think of the encoder as a reporter that's attached right to the motor shaft. As the controller tells the motor to move, the encoder is reporting back the shaft's actual position, hundreds, even thousands of times a second. So if the motor is told to move 90 degrees, but it only gets to 88, the controller sees that 2-degree error instantly and sends a little correction to finish the job perfectly.
Okay, but now think about this. What happens when something goes wrong? Let's say our conveyor belt jams up. That open-loop VFD just keeps pumping out power, totally clueless that the motor has stalled out and might be about to burn itself up. But with the closed-loop servo on our robot, if the arm gets stuck, the controller immediately sees that the position isn't changing. It knows there's a problem and can instantly shut down or send out an alarm. It's literally the difference between flying blind and flying with a full instrument panel. All right, so let's pull all this together. This all brings us to the final decision. How do you actually choose between these two really powerful technologies? So this is it, the final trade-off. And it's never about which system is better. It's about which one is right for the job. Look at position certainty. With a VFD, you're basically guessing the motor is where it should be. With a servo, you are confirming its exact position. And that means if the system stalls, the VFD just keeps running blindly, while the servo spots the error immediately. That's certainty. That's the key benefit. And that's what you're paying for with the more complex wiring and the higher cost. So let's boil this all down, right? Here's what you really need to remember. VFDs are your workhorses. They're for simple, cost-effective speed control. Think fans, pumps, those long-running conveyors. Servos, they're the surgeons. They're absolutely essential for high-precision, dynamic stuff like robotics and CNC machines. And the deciding factor for any engineer, it always comes back to one simple question. Is it good enough to assume the job is done, or do you absolutely need to know?
And that kind of leaves us with this really interesting question for the future. As all this technology gets smarter and cheaper, where are we going to draw the line between good enough control and perfect control? Is a day going to come when even the simplest devices demand the kind of self-awareness and certainty you get from a closed-loop system? Now that's the next frontier in smart control.